All right, we are now recording. Class has begun. Okay, so I've looked at the midterm exams. Uh, Now on Friday, I went over the majority of them because most of you had done them the night before. And then over the weekend, I looked at the ones that you guys turned in on Friday morning. So for the most part, they look very good. Um, the only consistent problem that I saw was that there were quite a few people who didn't calculate the gear ratio quite right. Most of you got it correct, but a substantial number of you had a little trouble calculating the gear ratio. I didn't take off very many points for that. I did have to take off a few, but not too many. We are going to talk more about that this week. In fact, so here's the plan for pretty much the rest of the school year, is that we are going to now talk in more detail about gear trains and other types of machines. Gear trains are just one out of many different types of machines that you need to know about if you're an engineer. And so that's the plan, is pretty much spend the rest of the year doing that, about machines. And in order to understand machines, you need to understand forces and energy and all sorts of other things. So that's what we're going to do. Okay, so as an introduction here, let me just pick one of the gear trains that was submitted that we didn't talk about on Friday. Okay, all right, so this was one that was submitted Friday morning. This was Cadence, and nice job. I like what he did. He approached it a little differently than most of the rest of you. Rather than having one support piece down the middle and then the gears on each side of it, he decided to put the gears down the middle and the support pieces on the outside, which is a great way to do it, and in fact has a lot of benefits. Maybe is a better way to do it. Okay, so here's his gears. You can see the handle right here. And so let's talk about how to calculate gear ratios, because a substantial number of you clearly didn't quite get that. So let's see how we did it. So on the same shaft that the handle is attached to, there is a gear, and that's the smallest gear, so that's the 8-tooth gear. So that 8-tooth gear is connected to the largest gear, which is a 40-tooth gear. Okay, so what that means is every time you turn the handle one complete turn, the shaft that the big gear is attached to is only going to turn less than that. And the ratio is going to be, 8 divided by 40, so 0.2, which is 1/5. So basically, you turn the handle one complete turn, this shaft is only going to turn 1/5 of a turn. Okay, and then Caden did something here that I think is quite interesting, and I'm glad he did it. You see how he's got two equally sized gears right here? So in that case, since the driver gear and the driven gear both have the same number of teeth, that's what we call a neutral gear ratio. So you're not gearing down or up in that case, and so you might wonder, why would you do it? Well, actually, there are some good reasons to do that. If the shaft here is too close to this big gear, it's so close that it's causing problems and you need to separate those shafts further apart, then doing what Caden did here is a very good way to solve that problem. Oh, oh no, Marshall, you are right. Um, that, oh, come on, is that a typo? Let me fix it. But okay, so that was just a typo. But you are correct. Let me fix that. Okay, there we go. All right. Oops. Now I need to. Okay, go back to here. Okay, so Marshall, thank you for catching that. Okay, are we good now? Okay. All right. So, okay. So this actually does serve a purpose. It does extend it over there so that so hopefully then you can get that shaft over there further away. Okay, and then now we have the last pair of gears where we have a 24-tooth gear connected up with the 16-tooth gear, which now in this case, instead of gearing down, it's going to gear up. Okay, And as we talked about on Friday, it's very unusual in a real machine that you would arrange it so that it gears down in one place and gears up in the other, because it's kind of counterproductive there. Generally, you decide ahead of time, do you want to gear down or do you want to gear up? And so you want to make it so that all of your pairs, all of your gear pairs, they all work in the same direction. They either all gear down or else they all gear up. You wouldn't normally mix it like this. But I didn't take off any points if people did this because I didn't talk about it like that before. Okay, so we have an overall spin multiplier here. Okay, so I got some windows in the way here. Hang on while I rearrange my windows. Okay, so we have an overall spin multiplier here of 0.3. So what that means is when we put all the gears together, okay, if we spin the crank one full turn, the output flag is only going to go 30% of a turn. Okay, and so this is something that some of you need a little more practice with, and that's okay, don't worry, we're going to get it. But now let's talk about more than just the spin multiplier, because most of the time when you are hooking up gear trains like this, the reason you're doing it is because you need to increase the amount of twisting force. Like for instance, let's suppose that you've got a car, just a normal passenger car, and you attach a trailer hitch and you want to pull a trailer or a boat or some heavy object. Okay, and now as you may know that cars and trucks, one big difference usually is the trucks have bigger engines because trucks are designed to pull heavy loads. Okay, so you've got this car which doesn't have this big strong engine, and you're trying to pull this trailer, and as long as you're pulling it on level ground, it's working fine. But you're trying to go up Parley's Canyon or up some other hill there, pulling this heavy trailer, you're going to find out that the engine of the car just may not have enough strength to get you up the hill. So what you do then is you want to put it down in a lower gear. You want to gear down. Okay. So what it does then is it multiplies the amount of twisting force. Okay. So sometimes when we talk about the multiplier, we are worried about the spin multiplier, but quite often, possibly even more often, what you really care about is the force multiplier. And the force multiplier is going to be the inverse of the spin multiplier. So if the spin multiplier is 0.3, the force multiplier is 1 divided by 0.3, which is going to be 3.3. Okay, so when you gear down, so if we were to take Caden's gear train here, okay, what we would find is that if we put a spinning force on the handle, then the output shaft is going to have a spinning force that is 3.3 times more spinning force than what we are doing. So it's increasing our spinning force. Now, it doesn't come for free. Nothing in this world comes for free. The price that we have to pay for increasing the force is that we have to spin the handle 3.3 times in order to get the output shaft to spin one time. But that's okay. That's a price we're willing to pay. All right. So this is what machines are used for. And by the way, we should start using the proper terminology. Whenever we're talking about a twisting force, a spinning force, it's really much more common, instead of calling it a force, a better word to use for it is torque. Okay. So a twisting force, we shouldn't call it a force, we should call it a torque. Now, there are people who call it a force because they say, well, twisting force and a pushing force, what's the difference? Well, okay, physicists, what we do in physics is when we talk about a force, we're talking about a linear force. So it's either a push or a pull. Now it might be a vertical push or a vertical pull, okay, but it's always a linear force. So whenever we talk about a twisting force in physics, we always call that a torque. So from now on, instead of calling it a twisting force, I'm going to call it a torque, so get used to it. Okay, so now let's look at a machine that I hope that you guys are all familiar with, a bicycle. Okay, so a bicycle is not that different from the gear trains that you guys have all worked with. David likes my foot. I'm glad to see that. But let me warn you guys, riding bicycles barefooted is a very, very bad idea. Please do not ride bicycles barefooted. Okay, so let's look at where the forces are, where the torques are, and let's just see, how this works, because this is what we're going to be doing now for the next little while. Okay. Oh, Van rides barefoot. Not a good idea, Van. Not a good idea at all. Okay, so the force, or let me rephrase that. The foot is going to exert a force, because what you're going to do is you're going to push down on the pedal. So that's a linear force. So it is legitimately called a force. Okay. So the downward force of the foot is going to cause a twisting force on the shaft here, and the amount of that twisting force can be different and will be different depending on a bunch of things. Okay, one of the things that it depends on is how long is the pedal arm. So the distance from the pivot point right here, the shaft, the axle, the distance from there to where the pedal is, that distance, that affects the amount of torque you're going to have. So if you have a longer pedal arm, you're going to be able to get more torque by using the exact same force. Now also the angle comes into play. We're going to talk a little bit more about this later, but okay, if this thing is up really high, so so it's as shown here, you're not going to get as much torque as you would if this arm right here, if this arm was out here vertical or horizontal. Okay, so imagine that this arm is horizontal. The same amount of downward force is going to give you more torque. So it's a little bit complex. I'll go into more detail later. Let's just continue on through here. So we got a linear force which causes a clockwise spinning force, which I'm now calling a torque, and and there is going to be a multiplier here. Okay, so now this gear is attached to a chain. Okay, so the chain is going to get pulled, and the chain is going to exert a linear force on the back wheel here. Actually, it's going to exert the force on the gear here. And so the force on that gear is going to result in a clockwise torque on the wheel. And the amount of clockwise torque here and the amount of clockwise torque in the front gear are going to be different. There's a multiplier in there. And the multiplier depends on which gear you choose for your front sprocket. And you see we got several gears we could choose for the back sprocket as well. Okay, so Van just piped in and said you can make the circle chain ring into an oval and make the torque constant. Yeah, so very nice, Van. I like that. Yes. Well, and now it may not make it exactly constant, but it certainly evens it out. Yeah, that's some advanced engineering, which I wasn't planning to talk about. Let's learn how to walk before we try to run. But you are correct, Van, that you can do some cool things if you shape those gears differently. Okay, so now we've got a clockwise torque here, and then now we got the wheel, which is connected to the same shaft there. So we got clockwise torque being transferred out to the wheel, and then where the wheel meets the road, then you get a linear force here. And the important thing is that according to your choice of gears on the front and on the back and everything, the amount of force that pushes the bike forward can and will be very, very different than the amount of force that you started with, your foot pushing down. So it's entirely possible you could push down with a force of, oh, I don't know, let's say 50 pounds. Let's say that you get your weight there, you're pushing down on there. So you exert 50 pounds of force on the pedal. The amount of force that gets transferred to the road that makes you go forward can and will be very different. It might be much more than 50 pounds, or it also might be less than 50 pounds. There are times when you want both. So let's say you want to go up a hill. Okay, so if you're going up a hill, you need it so that the output force here is a lot greater than the input force. So by choosing your gears properly on both the front and the back sprockets, you can make it so that your 50-pound force here ends up being 150 or 200 or 220 or some number that is substantially larger than the force that you exert with your foot. It multiplies your force by quite a large amount. But like I said before, it doesn't come for free. Okay, the price you have to pay if you gear it that way is that you have to spin this front sprocket. You have to turn the pedal a whole lot of times in order to go up the hill. Whereas when you're coming down the hill, or let's say you're on level ground, if you're on level ground, you don't need nearly as much force here, and you want to go faster. So then what you do is instead of gearing down, you're going to gear up. So then your force here doesn't get multiplied. In fact, it could very well be that you exert 50 pounds of force here, and the output force is only 25 pounds or 20 pounds, okay? But the advantage then is that you spin the front wheel one time, and then the back wheel spins a lot more than one time. So you don't need a lot of force. What you want is a lot of speed. Okay, so we're going to learn in detail how this works. Now, I don't expect you to be experts on it right now. Okay, but this is just to give you a flavor of what we're going to be doing for the next week or so. Okay. All right, now, what you see here is the front page of a book that is going to be our textbook for the rest of the school year. So I have the book in an actual hard copy paper form. What I've done for you guys is I have obtained an electronic copy, a PDF version of this book, and I have uploaded it to Canvas. Some of you may have seen already. I did it yesterday. So you have an electronic version of this book on Canvas, or as soon as you download it from Canvas, you'll have it. Now, the book contains a lot of information that is beyond what we're going to do in class. And so what I did was, when I uploaded it to Canvas, I did two different files. One was the entire book. If somebody wants the entire book, I put the whole thing on there. But it's a pretty big file. And so I figured, well, maybe not everybody wants that file. And so then what I did was I pulled out just the chapters that we're going to be using for the next couple of weeks. And I uploaded that as a separate file. So it's the same thing, but it's only the first couple chapters in the book. So it's a smaller file. Okay, so your homework for tonight is going to be to read from that book. And later I'll tell you what pages I want you to read. And then later we're going to be talking about the book, and we'll be doing some problems that they give in the book. And so basically that's going to be our textbook for the next little while, called Robotics Demystified. Okay. It's a pretty well written book. It's pretty easy to understand. It's written on a level that ninth graders should easily be able to understand. Here, what you see here is the first couple of pages from the contents. And so what you're going to see is that in chapter 1, they talk about robots in general, a little history of robots. It's not something that's vital, and so I'm not going to require you to read chapter 1, but I do think it's interesting. I would recommend that you read chapter 1, but if you don't read it, it's not going to be a problem. I'm not going to put things from the test on there. Or rephrase that, I'm not going to put things from there on the test. Okay, but it is kind of interesting. Okay, so chapter 2 is what we're going to jump right into. Chapter 2 talks about some things that you need to understand in order to understand how machines work and gear trains and whatnot. So you'll see that some of the things we're going to be talking about are energy. We're going to talk about units of measurement for position, time, length, mass, velocity. We're going to talk about acceleration, what that is. And very importantly, we're going to be talking about forces. And you can see there's more stuff going on here. So if you don't understand these concepts, and you have no hope of understanding machines, which is in chapter 3, which is what we're going to do next week. Okay, so the gear trains that we've built, we're going to talk more about those and other types of machines. But before you can really talk about them, you need to first understand the stuff from chapter 2. All right, so that's what we're going to go into. Now, I think the book does a pretty good job of describing what you need to know. but there are a few things that I think it could do better. So what we're going to do today is I'm going to talk about the few things that I think the book could have done a little bit better job on, and I'm not going to talk about the things that I think the book does do a good job on. I'm trusting that you can read for yourself. Remember, one strong philosophy that I believe in is that it's not the teacher's job to read the textbook for you. It's your job. It's just the teacher's job to pick out the things that I know based on my experience students have a little bit of trouble understanding. Those are the things we're going to talk about today. Now, before I jump into that, further on in the book, okay, in chapter 4, it talks about electricity and electrical circuits. Hey, we've already covered that. You guys should now be experts, at least in basic electricity. Now, obviously, there is much more advanced stuff we can go into, but right now, I think you guys understand electricity and electrical circuits well enough that I'm not planning to go into it. So chapter 4, you shouldn't need to read. You're all, of course, welcome to if you want to. Also, chapter 7, they talk about programming. And again, that's something that we've already gone into, the Arduino. You guys hopefully now are really good at programming Arduinos. So that is something that is vitally important to know, but I think you guys are good on that. But chapter 7 talks a little bit. Now, chapter 7 doesn't talk specifically about Arduinos. It talks about it in more general details. So it might be interesting. But not essential. So Van is asking, is this now a physics class? The answer to that is, hey Van, everything is a physics class. Biology, that's just applied physics. Chemistry, that's just applied physics. Yeah, everything is a physics class. Okay. Now somebody might argue that history might not be a physics class. Okay, that one's gonna be a little bit argue. English, okay, that might be a little difficult too. Okay, but okay. So, what about standard math? Yeah, well, okay. Now Sky brings up a good point. Sky argues that maybe physics is really just applied math. And I think Sky may be onto something there. Yeah, but let's not worry about that. Okay, so here, what you see here are some topics that we need to talk about, that you need to know. These are topics that are discussed in chapter 2 of the book. And like I said before, I think the book does a pretty good job of describing most of these. Um, the one thing that the book leaves out, which I think is really important, is the special kind of force called torque. The book talks a lot about pushing forces and pulling forces. It doesn't talk so much about twisting forces, which, as you now know, are more properly called torque. So let's talk a little bit about torque. All right, so hopefully you guys have all had experience where you take a wrench and put it on a nut and you twist the nut. Now this is a kind of a strange looking wrench because it's a cutaway view of the wrench. So normally the wrench would cover up more here. And so whoever did the drawing here, which by the way wasn't me, I downloaded this from the web. Whoever did the drawing did what's called a cutaway, so it's a little easier to see. Okay, so what's happening here is the hand is pulling on the wrench. So that's a linear force. So that legitimately can be called a force. Okay. So that linear pull from the hand gets translated into a twisting force on the nut. And that twisting force then is what we call the torque. Okay. And here is the official definition of torque. So right here, this is the pivot point. This is where the nut would be. This bar right here that has a length D, that is the handle of the wrench. And this red arrow here, that's F, that's the force, that is the linear force of the hand pulling on the wrench. And so the correct way to calculate how much torque, how much twisting force is going to be exerted is given by this equation right here. This fancy looking T that you see here, it looks like a kind of a cursive type T, that's actually the Greek letter tau. And so that's what's usually used for torque. So the Greek letter tau, which you can call it a cursive T if you want, Okay, the way to calculate that is take the amount of force, and force here in America, force is usually measured in pounds, although in other countries, it's in more civilized countries, it's called, the force is measured in newtons. But here in Merca, it's measured in pounds. So we take the number of pounds of pulling force that the hand is doing, we multiply that by how far, how many feet is the distance here. Now we could use inches if we want, but in America the standard unit is feet, okay? And then we've got this thing that some of you are going to recognize and some of you are not going to recognize. So this thing right here, it says sin theta. So some of you who've never met that, never seen that before, you might say sin. What do you mean sin? Did somebody do something evil here? Did they sin? And hopefully others of you know. Okay, good. I see the sky knows. It's really called a sine. And I see Daniel agrees with that. Okay, so the official name of it is sine. It's just abbreviated SIN. Okay, now, some of you who are in Math 1 right now may not have learned about sines and cosines and tangents and other trigonometric functions. But I do know that several of you do know about them. Subway. Okay, John, I have no idea what you meant by that comment. Okay. All right. Okay, so anyway, because a lot of you guys haven't learned about sines and cosines, I'm going to make it easy for you. Okay. So Marshall measures in hamburgers. Hey, Marshall, guess what? Hey, wait a couple slides here, and I have something just for you, Marshall. I'm glad to see you measure in hamburgers because so do I. You'll see what I mean in just a few minutes. Okay, but let's get back to this. Okay, so if this angle here is all, hey, relax, guys, relax. Okay. Those of you who are not participating live, those of you who are watching the recording, you're not going to have any way of knowing what's going on here because in the recording it doesn't show the comments. But I'm getting a lot of really strange comments right now about Marshall saying he measures in hamburgers. David is saying something about bald eagles and shotguns and forests. So I'm not quite sure what's going on here. But okay, let's get back on track here, guys. Okay, so if this angle here is always 90 degrees, then you don't need to worry about the sine of theta. What you can do then, you can just say that the torque is equal to the force times the distance, and you don't have to worry about sine theta. Now that's only true if theta is going to be equal to 90 degrees, but because I'm such an incredibly nice guy, all of the problems that I'm going to give to you guys to do, theta will always be 90 degrees. Okay, so Daniel, you're saying you're lost. Is there anything that I could do to help clarify? Well, actually, tell you what, I'm going to give you some examples. Okay, hopefully the examples that I do will help you. So don't worry about sines and cosines. We're not going to do that in this class. Oh, I see you're lost with the other chat things. Okay, well let's forget that. Let's get back on track here, guys. Okay, so just keep in mind what I say right here. So if this angle here is 90 degrees, which it will be for all of the problems that we do in this class, then you can replace the real formula for torque with this simplified formula. The torque is just equal to force times distance. So everybody write that down in your notebooks. Remember that the amount of twisting force you get, the amount of torque, is always going to be whatever the linear force is of the hand, okay, however many pounds of force that is, multiplied by the distance from the hand to the pivot point, which is what's sometimes called the lever arm, okay? All right, so let's do a problem here. Let's, oh, I'm sorry, before we do that, let's talk about units here. Okay, so like I said a minute ago, here in America, most people, they measure forces in pounds, which is abbreviated as LB. And there's a historical reason for why it's LB. I don't want to go into it now. But in other parts of the world, in fact, in almost everywhere in the world except for America, the pulling forces are measured in newtons, okay? And so now you might say, okay, well, how many newtons is equal to a pound? All right, so a pound is approximately equal to 4 newtons. Okay, actually it's a little bit more, it's about 4.4, but hey, let's not get too technical here. Let's just say a pound is approximately 4 newtons. Now I'm trusting that most of you guys have a feel for how many pounds something is. If I take this book, you know, hopefully you should know that this book is clearly not 100 pounds. You know, it's maybe 2 or 3 pounds, you know, or, hopefully you have a feel for how much a pound is. So I like to think in terms of, you know, something that I can relate to. And Marshall, here, this one's for you, okay? If a newton is about 1/4 of a pound, so Marshall, you like hamburgers, right? Okay, so anybody go to McDonald's and order the 1/4 pound hamburger at McDonald's? Okay, so now when McDonald's sells you a 1/4 pounder, that 1/4 pound is the weight of the meat, not the weight of the entire hamburger. Okay, so if you want to know how much is a newton, just imagine a McDonald's 1/4 pounder where you just take the meat only, and so the weight of that's how much a newton is. Okay. Now we are going to be using both units interchangeably because engineers need to be fluent in both languages, both the metric system or metric language, if you will, and the metric system or the metric language. Think of it as a language. So you guys need to know both. So in some of the problems that I'm going to have you do, I give you the units in pounds and in feet, and in other of the problems that we're going to do, instead of pounds, we're going to do it in newtons, and instead of feet, we're going to do it in meters. Okay. All right. So forget newtons, I'll call it a 1/4 pounder patty. Okay. All right, we can do that. Okay, so now here is a problem kind of like you might possibly see on today's daily quiz, wink, wink, nudge, nudge. Okay. So let's suppose that the hand is pulling on the wrench and it's pulling with 30 pounds. Now, do you guys agree that that's a reasonable number? I mean, you hopefully have a feel for how much 30 pounds is. And yeah, I think it's reasonable that an average person would be able to pull with 30 pounds of force. In fact, a lot of people should be able to pull with more. Okay, and let's suppose that the wrench, the handle on the wrench is 6 inches long. Okay, now we're going to be working in feet. That's the more standard unit for engineering is feet. So instead of calling it 6 inches, we're going to call it 1/2 of a foot. Okay, so then the question, how much torque is, and so I see that you guys are way ahead of me, which is a good thing. So Daniel is saying that the answer is 15. And so David is saying that it's 15 pounds, okay, or about 60 newtons. But now, hang on, remember about units, okay? Remember the definition of torque, okay? Torque is defined as force times distance. So let's look at the units then. Force is measured in pounds. Distance is measured in feet. So this 15, which is the correct number, is not going to be 15 pounds, it's going to be 15 pound-feet. Or what's more commonly done is they switch them around. So if you're talking with an engineer and you say the amount of torque is 15 pound-feet, the engineer is going to look at you a little weird because usually they say foot-pounds rather than pound-feet, even though it really means the same thing. Okay, so the common way to express the answer here is we would say the amount of torque is 15 foot-pounds. Okay, so get used to that. Now, if you said 15 pound-feet, I wouldn't mark it wrong because, you know, when you're multiplying, it doesn't really matter. 3 times 4 is the same thing as 4 times 3. So a pound times a foot is the same thing as a foot times a pound. Okay, all right, so the answer is in fact 15 foot-pounds. Okay, pretty heavy feet. Yeah, they are. Okay, all right. So that's torque. Oh, and by the way, let me go back up here again. So don't be surprised if instead of saying 30 pounds, I might say 100 newtons. And instead of saying a half a foot, I might say 0.7 meters. So in that case, what would the units be? How would you respond if this was 13 newtons instead of 13 pounds, and if this was a half of a meter instead of a half of a foot? The answer is still going to be 15. Okay, very good, David. You got it exactly right. It's going to either be Newton meters or meter newtons. And again, it doesn't really matter. So the convention is we usually say Newton meters. Although, if you wanted to say meter newtons, that'd be fine. Okay, so if this was newtons and that was meters, the answer would be 15 Newton meters. Okay, so the book doesn't really talk much about torque. I just did. I will hold you guys responsible for knowing about torque. So I hope that you took careful notes. If you didn't take careful notes, then I hope that you go back and watch the recording of this video, which I'll post soon after the class is over. Okay, now there's one other thing. Now in this case, the book does talk about this, but I know from experience that students sometimes struggle with this. So vectors and scalars, those are words that might be new to many of you. You need to know what is a vector and what is a scalar, how are they different. This is very important. Okay, now the book does talk about it, but I'm going to go into it anyway, just make sure that we do it. But let me start off by asking you guys a simple question. What is 2 plus 2? Okay, so I see Daniel says 4, Dan agrees, Van says 4. Eve says it depends, okay? Because Eve knows me, and she knows what a tricky devil I can be. So she is thinking that maybe there might be some circumstances where 2 plus 2 might not be equal to 4. Now, if your math teacher says what's 2 plus 2, the answer is definitely 4. But let's look at a situation where 2 plus 2 might not be equal to 4. Okay, so let's start. Okay, let's start by saying I've got some object and somebody is pushing on that object. Let's say I've got two people, so I've got A and B. So A, let's say, is a girl named Alice, and B is a boy named Bob. Okay, so here is a rock. Alice is pushing on it, and she's pushing with 2 pounds of force. Bob is also pushing on the same rock, and he's also pushing with 2 pounds of force. But what is the total force going to be on the rock? So what I really want to know is what is the answer, what is force A plus force B? So in essence, I'm asking what is 2 plus 2, but really the way I have to word it here is what is force A plus force B going to be equal to? Do you see now that it's entirely possible that it might not be 4? Okay. If Alice and Bob are both pushing in the same direction, then yeah, the answer will be 4. The total amount of force on the rock will be 4. Okay. But what if Alice and Bob are pushing in opposite directions? So here's the rock. Alice is pushing this way with with 2 pounds of force. But Bob is pushing the opposite direction. You see they're going to cancel each other out. So the total amount of force on that rock could be 0. So 2 plus 2 could in fact equal 0. So Daniel, I noticed you typed in, huh? So does this clarify it? Do you see how that when you're dealing with forces, 2 plus 2 is not necessarily equal to 4? Did I clear things up for you there, Daniel? Okay. And it even gets more interesting. What if Bob is pushing horizontally and Alice is pushing vertically? In that case, 2 plus 2 does not equal 4 and also does not equal 0. In this case, it equals 2.8. Actually, it's 2.8 something, 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 something. It's actually the square root of 8. Hopefully you guys can figure that out. Okay, so the reason I bring this up is because when you're dealing with forces, you can't just say that the force is 2 pounds. That does not adequately describe the force. In order to completely describe the force, you need to not only tell the strength of the force, which by the way is commonly called the magnitude. So this is a word that you need to get used to, because boy, am I going to be using this word a lot. So the strength of the force is the magnitude. So that's the number part. That would be the 2. Okay. But you also have to tell what direction the force is going. Otherwise, you have not completely specified the force. So whenever you have some quantity like that, where in order to completely describe it, you have to tell not only the magnitude, but also the direction, that thing is called a vector. Okay. So forces are vectors. So if I'm pushing on some object, I need to say I'm pushing with 53 pounds and I'm pushing in the direction that's to the west. Otherwise, I haven't given you enough. Okay, I see that David has apparently seen the movie called Despicable Me. Yes, okay. So if any of you guys have seen that movie, you know there's a guy in that movie named Vector, and his catchphrase is, committing crimes with both magnitude and direction. You remember that line from the movie? So he commits crimes with both magnitude and direction, and his name is Vector. Okay, so yeah, that's a good way to remember it. Okay, so Luke is asking whether we're going to use polar form or component form. We're not going to be using component form here. What I'm going to do is I'm going to give you the magnitude, and then I'm going to use words to describe the direction. Okay, so now, here are some examples of forces where I have completely described the force. You know, it's 3 pounds to the west, or it's 2 pounds to the north. Or, in answer to Luke's question here, if it's off at a funny angle, I'm going to say that it's 4 pounds of force directed at a direction of 35 degrees north of east. So get used to that. Now, Luke realizes that there are other ways that you can describe forces, and there's a thing called components. We're not going to do that in this class. That's beyond what I intend for you guys to do. Okay. Now, there are many other things in this world where if you said that you know, what is the temperature, and you said, well, it's 98.6 degrees to the west, people would say, huh? That would make no sense, right? Or if I said, how much mass does this thing have? And you say, well, 79 kilograms to the south. That makes no sense, right? So things like time and mass and temperature, those are things where direction makes no sense. So all you have in that case is just the magnitude. So this is kind of the opposite of a vector. So those things are called scalars. Okay, so these are 2 words that you definitely need to know. You will probably see them on today's daily quiz, and I guarantee we'll be using them later on in the year. So hopefully you guys understand the difference between a vector and a scalar. A vector, you have both magnitude and direction. A scalar, you only have magnitude. Direction doesn't make sense. So forces are most definitely vectors. Okay, well, we've covered everything that I think is important for today anyway. Your homework for tonight, as you can see right here, is you need to download this guy, the electronic copy of this guy. If you want to download the entire book, go ahead. I mean, it's not that big of a file, and that's what I would recommend. But if you want, you can just download the smaller version that's just the first 3 chapters. And then I want you to read pages 13 through 25, and then be prepared to discuss them next time we meet. So what I recommend is when you're reading along, I want you to keep a piece of paper by your side there. And whenever you come across anything that you don't fully understand, just write a little question down on it. And come to class prepared with questions that you can ask, where you say, hey, on page 17, they said this and they didn't really make sense. Can you please explain that? That's what we're going to be doing next time. And then later we'll have quizzes on it, but not too much. So for today's daily quiz, which by the way, whenever we have a class here, we also have a quiz. So today's daily quiz, you don't need to do the reading before you take today's daily quiz. Today's daily quiz will only we'll only ask questions about things that I have just talked about in today's class. Okay, so Van is saying not every time. Okay, maybe not every single time, but almost every time that we do. Okay, so that's pretty much it. Does anybody have any questions about what we talked about just now? Nope. Okay. All right, so, oh, secret word. Yes, good point. Secret word. Yeah, I don't want to forget about that. See, I didn't bring my marker here. Anybody want to prepare one? Grub, we already used grub. Slorp, okay, I like that, slorp. Okay, so let's go with slorp as the word. Okay, so S-L-O-R-M-P. Okay, can you see that? Okay, so S-L-O-R-M-P. Okay, and by the way, Sky, is that is that a real word in any language, or is that just a totally made up word? Okay. All right, so anyway, that's the secret word for today, just totally made up. Okay, well, that's fine. There's no law that says the secret word has to be an actual word. Okay, so I think that's about it. If nobody has any more questions, so let's see. So going once, going twice,